Hello, and welcome to the next video in my series on basic statistics. And for this video, finite mathematics. The topic of this video is taught in both stats courses and finite math courses. So you may be watching this in a stats playlist or in a finite math playlist. But either way, it does apply to both. Now, a few things before we get started. Number one, if you're watching this video because you are currently having problems in a class, I want you to stay positive and keep your head up. If you're watching this, it means you have come pretty far in your education up to this point, and you may have just hit a rough patch. And I know that with the right amount of hard work, patience, and practice, you can get through it. I have faith in you, and so should you. Number two, please feel free to follow me here on YouTube and or on Twitter. That way when I upload a new video, you know about it. And on the topic of the video, if you like it, please give it a thumbs up. That does encourage me to keep making them. If I know individuals find them beneficial, I want to keep doing them. On the flip side, if you think there is something I can do better, please leave a constructive comment below the video, and I will try to incorporate that in the future videos. And finally, just keep in mind that these videos are geared towards individuals who are relatively new to stats, or finite math for that matter, so I will just be going over the basic concepts very slowly and very deliberately. I want you to know what's going on, but I also want you to know why it's going on. So all that being said, let's go ahead and get started. Now, this video is the next in a series on probability distributions. So in previous videos, I talked about discrete probability distributions in great detail. We looked at coin flips, we looked at die rolls, among other things. So the binomial distribution is a specific type of discrete probability distributions. And remember, a discrete distribution just means that the numbers or the outcomes can only have a finite number of outcomes, and they are almost entirely whole numbers like 1, 2, or 6, or whatever. They're not going to be like 47.895. So a discrete probability distribution means that each outcome is usually a whole number, and it also means there are a finite number of outcomes, or a infinite sequence of numbers like 1, 2, 3, 4, 5. But again, that's in a previous video. I don't want to go into all that right now. So if you'd like to have some sort of refresher on discrete probability distributions, go back and look at those videos. Now, to understand the binomial distribution, we're going to be using an example. And this example is about the performance of salespersons we manage. So we're going to get at the binomial distribution by looking at how two salespeople on our floor do in terms of closing sales and their productivity and how many sales calls they make per day. So we're going to get at this concept through a problem. So let's go ahead and take a look at that problem. So here's our example. You are a sales manager. And of course, as the sales manager, you analyze the sales records for all salespersons under your guidance. So you look at how many sales calls each person makes. You look at how many successful sales they make, how many closes they make relative to their calls. And you look at their productivity, how many calls they make per day, and things of that nature. So right now, you're going to be looking at two individuals on your sales floor. Joan has a success rate of 75%. So if she calls someone during the day and she makes her sales pitch, she closes that sale 75% of the time. That's really good. And she averages 10 sales calls per day. Because these are not just quick 1-minute sales calls. These are more involved sales calls that your employees make. But she makes 10 per day, and she closes about 75% of them. Now, Margot has a success rate of only 45%, so much lower. but she averages 16 calls per day. So different success rates and different average call counts per day. So here's the question. What is the probability that each salesperson makes exactly 6 sales on any given day? So what is the probability that Joan closes 6 sales on any given day, given her success rate and average number of calls? Same thing for Margot. What's the probability that she makes 6 successful calls per day, given a rate of 45% and 16 calls per day? So that's going to be the question we answer at the end of this video using the concept of the binomial distribution. Now we can begin understanding the binomial distribution by looking at the binomial experiment. And this is a specific kind of experiment that has very specific instructions or details to it, or conditions. Let's go ahead and look at this. So a binomial experiment has the following characteristics. Number 1, the process consists of a sequence of n trials. So we're going to call these iterations. So if we have a sequence that is 6 trials, we have the first iteration, the second iteration, the third, fourth, fifth, and sixth. So 6 trials. And that number of trials is fixed. So whatever our n trials is. Number 2, the process only has 2 exclusive outcomes. One is called a success, and the other is called a failure. Much like a coin flip can only have heads or tails. This binomial experiment can have a success or a failure, and those are mutually exclusive. Now there is an asterisk to this condition, which I'll talk about at the end. Number 3, the probability of success is denoted by a lowercase p, and that probability does not change from trial to trial. Now the probability of failure is 1 minus p, because remember the probabilities have to add up to 1. So if success is p, then failure is 1 minus p, or 1 minus that success. And it's also fixed from trial to trial. So this fixed nature of the probabilities is very important. Because think of a coin flip. The probability of heads is 0.5, the probability of tails is 0.5. Do those probabilities change from flip to flip? Well, no, they remain fixed. And so is the case in the binomial experiment. Of course, they won't always be 0.5 and 0.5. They might be 0.25 and 0.75, or 0.1 and 0.9. But they do remain fixed. And finally, the trials are independent. The outcome of a previous trial does not influence the next trial or future trials. So again, think about a coin flip. If I flip a coin and tails comes up, does the fact that tails came up that time influence what comes up next time? Well, no, it doesn't. And that's because each coin flip is independent. Same thing for this binomial experiment. So this is very similar in a way to coin flips, because on a coin, the probabilities are fixed. There are only 2 of them, and they are independent. And of course, in the binomial process, we have a sequence of flips, or sequence of trials. Now here's the asterisk. If you look at number 2 up there, we have one outcome is success, one is failure. But success and failure can be counterintuitive if you take them literally. A success doesn't always mean it's a positive outcome. A success is really whatever characteristic we're looking for. And the failure is the opposite of that. So don't think of success and failure as good and bad. It doesn't always work that way. So let's look at an experiment involving 5 trials. So our n equals 5. Our interest is in the number of successes in n trials. So what we do is we establish a discrete random variable, x, to represent the number of successes in our trials. So let's think about this. We have an experiment that has 5 trials. We're interested in the number of successes in those 5 trials. So we could have 0 successes, we could have 1 success, 2 success, 3 successes, and so on. And of course, the opposite is the failure. So if we have 0 successes, that means all 5 had to be failures. If we had 3 successes, that means the other 2 had to be failures. So you can kind of see how this works. So the number of successes can take any number, 0, 1, 2, 3, 4, or 5. We could have 0 successes all the way up to all 5 being successes in these 5 trials. So let's look at one version of the experiment. So we have different iterations, so 1, 2, 3, 4, 5. And at the first iteration we have a success. Then the next one we have a failure. And then we have a failure again. Then we have a success. Then we have a failure. This is a lot like a coin flip being tails, heads, heads, tails, heads, or whatever it might be. So success, failure, failure, success, failure. So we have 2 successes and 3 failures in that experiment. Let's look at another one. In this one we have success, success, failure, success, success. And those are our 5 trials. So in this case we have 4 successes and 1 failure. So you can kind of see how this system of trials works. 5 trials, because our n is 5. Each outcome can either be success or failure, and they are independent. So let's look at the case of 4 successes and 1 failure. Now the thing about this is that failure can occur at any of the 5 iterations. So look at this. In this case, the failure is in the 3rd iteration. In the next row, the failure is in the 1st iteration. In the next one, it's in the 4th. In the second from the bottom, it's in the 2nd, and then it's in the last. So the failure can occur in any of the 5 spots of the trial, which means the successes can't occur in any of the other 4. So remember, we're interested in the successes. So how can we represent this? We can look at this chart and say, well, there are 5 different ways we can have 4 successes and 1 failure. So how do we do that in mathematical notation? Well, 5 choose 4. So if you remember our combinations video, this is where it comes into play. So what we're saying here is there are 5 trials. We are interested in the 4 successes. But those 4 successes can be in any different 5 combinations. In the top one, the successes are in 1 and 2 and 4 and 5. In the second row, the successes are 2, 3, 4, 5. In the third one, they're 1, 2, 3, and 5, etc. So there are 5 different ways to have 4 successes in these 5 trials. So 5 choose 4 equals 5. And we can actually see them there in that chart. So let's go ahead and fill out our chart. This is for every combination of success and failure. So in the first column we have n, which is our number of trials. That's always 5. In the second column we have the number of successes. So 0, 1, 2, 3, 4, and 5. Now the number of failures is the difference. So if we have 0 successes, we have 5 failures. If we have 1 success, we have 4 failures. If we have 2 successes, 3 failures, and so on. Now in the combination column, remember, we're interested in successes. So in the top column, we have 5 choose 0. How many ways can we do that? Well, 1. Because remember, 5 choose 0, that's 0 successes. So that means all 5 are failures. Well, there's only one way to do that. Failure, 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 failure. Now, successes, how about 1, and failures 4? Well, that's 5. Choose 1, because we're interested in the successes, and that is 5. Now let's skip down to 3 successes and 2 failures. Well, that is 5. Choose 3, because those 3 successes can be in the chart in 10 different ways. So this is just simple combinations, where the first number is the number of trials, and the second number is the number of successes. 5 choose 0, 5 choose 1, 5 choose 2, etc. So the totals are 1, 5, 10, 10, 5, and 1. So let's take this further and look at another problem. Okay, and this will get towards our final problem. So a very poor, a very bad one, a manufacturer is making a product with a 20% defect rate. So 20% of the product being produced is defective. That's bad. Now, if we select 5 randomly chosen items at the end of the assembly line, what is the probability of having 1 defective item in our sample? So, when I run this type of problem past my students at first, they blurt out with an answer. They say, well, let's see, 1 out of 5 is 20%, so the probability is 20%. I'm like, no, it's not. It is not 1/5 or 0.2 or 20%. Because remember, each time we take something off the end of the assembly line, that is an individual trial. It's either defective or it's not. Then we take a second item. It's either defective or it's not. Then we take a third item. It's either defective or it's not. All the way up to our 5 items. So note, this is where success and failure are counterintuitive. In this example, a success is a defective product, because that's what we're interested in. So think of success as the item or characteristic of interest more than success, because in this case, the success is a defective product. So the number of trials are 5, because we're selecting 5 items at the end of the assembly line, maybe like every hour throughout the day or something. And the number of successes, which is a defective product, is 1. So what is the probability of having 1 defective item in our sample? So, as we talked about in the previous slides, this is 5 choose 1. So think about this. I want you to think about doing it. So the first hour we go up to the assembly line and we pick a product off the end of the assembly line. Well, it's either defective or it's not. Let's say it is defective. Well, that would be our 1 defective product. And then to meet this criteria, the next 4 would be not defective. Or we can select one off the end of the line and it's not defective, but then the second one is defective. Or we could do it again and the third one is the defective one. Or we could do it again and the fourth one is the defective one. Of course, again, and the 5th one is the defective one. That's why there are 5 different ways to do that. That's where we get our 5 choose 1. So just a reminder, a success is a defective product. So here's how that could work. Now, remember, a failure is a good product and a success is a bad product. So we could have these 5 outcomes. Our defective one could be the third one. Our defective one could be the first. Our defective one could be the 4th one we pick. Our defective one could be the second one, or it could be the last. So that's why we have the 5 choose 1. So let's put in some numbers here. Remember, our probability of being defective, which is actually a success, is 0.2. Therefore, the probability of being a good product is 1 minus p. I'm sorry, that should say 1 minus p, is 0.8. So in the places of the S and the F, we just put in those probabilities. So this is exactly like the last chart, but we take the S's and we put a 0.2. We take the F's for failures and we put 0.8. Now remember, to find the probability of this occurring, of this trial sequence, we just multiply the probabilities together. So let's look at the first row of this outcome. So we go up to the assembly line, and the product is either going to be a successful, or failure. So we pick up the product and it's good. The probability of that happening was 0.8. Then an hour later we grab another one. The probability of that being a bad product was 0.2. The probability of being a good product is 0.8. So it's good, so that's 0.8. Then we pick up the third one. Well, that's defective. The probability of that happening was 0.2. Then we pick the fourth, that's okay, so 0.8. The fifth one's okay, 0.8. Now the probability of that sequence in our trials of happening is 0.8 times 0.8 times 0.2 times 0.8 times 0.8. And then we add those up, or multiply those together, I'm sorry, and we have 0.08192. So that's a very specific outcome. We have failure, failure, success, failure, failure. The probability of that happening is 0.08192. Now look at the second row. Well, all we've done here is rearrange the numbers. In this one, the success, or the defective product, comes first. But the multiplication doesn't change. It's still a 0.2 and 4 0.8s. So we multiply that together and we get the same thing, 0.08192. Look at the third row. In this case, the defective one is the fourth one. But again, the math doesn't change. It's still 4 0.8s and a 0.2. That is 0.08192. So you can see the pattern here. Just because we arrange the numbers differently in each outcome doesn't mean the probability changes. And that's important. So we have 5 choose 1 over on the left because we have 5 different outcomes for this one defective product. And each outcome has its own probability, which happen to be the same because the numbers are the same. So what we're getting at is a general formula. If you look on the lower left, you can see this crazy looking general formula. And that is just the formula without the numbers in it. So don't freak out. So remember, N is our trials, X is our number of successes, and P is our probability of success. So we can just substitute everything in. So what we have here is 5 is the N, that's our number of trials. 1 is the number of successes we're interested in, so we're interested in 1 success. Those are the 0.2s there in our chart. Now, of course, there's 5 ways to do that. So 5 choose 1 is 5. That accounts for all 5 rows in our chart up there. But then in each row, it's the same thing. So we have 0.2, and then we have 4 0.8s. So we can just do that using exponents. So 5 choose 1 times 0.2 to the first times 0.8 to the fourth. And again, that's just simple multiplication, but we used exponents to make it easier to write. Now when we go ahead and do that, we have 5 times 0.08192, which equals 0.4096. And again, that's the same thing as adding up the probability column over there. So, what can we conclude? Well, in this case, the probability of selecting 5 products randomly, okay, in a sequence. So we walk up and pick one, then we come back and pick one again, and we come back and pick one again, etc. 5 times. The probability of having one defective product in that sequence or in that experiment is 0.4096, or almost 41%. See? So, if I walk up to the assembly line 5 different times during the day, I pick a product, and I do that 5 times, the probability of having one defective out of that 5 is 0.4096. See, and here's where you got to think differently. The defect rate is 20%. So you would think that, there would be one in there, and that would be sort of 20%. But because these are individual trials, so each trial is a choice. That's why it's 0.4096. You got to think of each trial as its own thing. So here's our general formula, which we already covered. So n is the number of trials, x is the number of successes, and p is the probability of successes in any given trial. So in that previous example, we had n equals 5, number of successes was 1, and our probability of success, which was a defective product, was 0.2. So we just went ahead and plugged that into our formula, and we came up with 0.4096, or about 41%. So the probability of one defective product in 5 trials of selection is about 41%. So now, what if we do this for each possible number of successes? So remember, we can have 0 successes or 0 defective products. We could have 1 success or 1 defective product when we do that experiment, 2, 3, 4, or 5. So all we do is change the numbers in that formula. So you can see in the calculation column we have 5 choose 0 and 5 choose 1, 5 choose 2, because that's the number of successes. And then the exponent above 0.2 changes, because that's p, that's our number of successes. So as we have 1 success, the exponent's 1, 2 successes, the exponent's 2, etc. Now with the failures, we have 0.8. That's the probability of failure. And then the exponent changes to match that. Notice that the exponents always add up to the number of trials. So 0 plus 5 is 5, 1 plus 4 is 5, 2 plus 3 is 5, etc. So we just have the combination part, then we have the success part, and then the failure part of this formula. And then from there, it's just math. So we have the probability of 0 successes, which is the same thing. The probability of having no defective products is 0.32768. Then we move on down. The probability of having 1 defective product, or 1 success, is 0.4096. That's what we found out in the previous one. Then we can go down. 2 defective products, 0.2048. 3 defectives in that 5, 0.0512. 4 defectives, 0.0064. And then finally, the probability of all 5 of our selections being defective is 0.00032. A very small probability. And that should make sense. Even if we have a defect rate of 20%, the probability of going up to the end of the assembly line at 5 different points during the day and selecting a product, and all those products being defective, is very low, 0.0032. Now if you notice, if we add up that probability column, what does it add up to? 1. It adds up to 1. So let's look at this in a chart. So here's our quality control. Remember, our defect rate was 0.2, so that's actually a success. That's P. And N was our number of trials. So along the left-hand side, we have probability. And along the bottom, we have the number of defective items, because that's our success. So 0 defective items, 0.32768. 1 defective item, 0.4096, and then so on and so forth. So this right here is the graph of our discrete probability distribution, our binomial distribution for our quality control problem. Let's go ahead and look at our first example, and then we're done. So here's our original problem. Remember, we have 2 salespersons. We have Joan and Margot. Joan has a success rate of 75% and averages 10 calls per day. So that's our trials, 10 trials. Margot has a success rate of 45%, but averages 16 calls per day. So those are our success rate and our number of trials. and we're interested in the probability of 6 sales. Let's look at Joan. So here is our general formula. So N is number of trials, X successes, and P is probability of success. So for Joan, the trials are 10, the number of successes we're interested in is 6, and the probability of success, in her case, is 0.75. So we can go ahead and insert these into the formula. Then we go ahead and do that. For Joan, the probability of closing exactly 6 sales during any given day is 0.146, or 14.6%. That is the probability in the percentage of Joan closing 6 sales on any given day. Now let's look at Margot. So same general formula, but her trials are 16 because she makes 16 calls per day. Number of successes is still 6. The probability of success in her case is 0.45. So we go ahead and insert those into our general formula. Do the math. And the probability of 6 sales for Margot is 0.168, or 16.8%. Now, is it higher or lower than Joan? Well, it's higher, isn't it? It's higher. So we have two things going on. We have success rate and the number of trials they're doing each day, or the number of calls. So even though Margot's success rate is much lower, the fact that she's making more calls makes up for that. And that's what's kind of really cool about these type of problems, because you would think that Joan would have more success, but really it's Margot because of her greater number of calls made. So let's look at these two together. So on the left we have Joan's binomial distribution. And you can see that the height of each bar is the probability of making that specific number of sales per day. So you can see in the green bar, her probability is just below 0.15. But if we go over to Margot, we can see that hers is way above 0.15. It's nearing like 0.18 zone, or 0.17. So 6 sales, Margot has the edge in 6 sales. So for Joan it was 0.146. For Margot it was actually 0.168, or about 0.17. And that's the green bar. Now, what about the probability of making 8 sales in any given day? So now look at the blue bars. Now for Joan, that's way up there. That's between 0.25 and 0.3. So we can say about 0.28 probability for making 8 sales. Now what about Margot? Well, 8 for her is below 0.2. It's way down there. So for 8 sales, Joan's probability is 0.282. For Margot, it's 0.181. So for 8 sales, Joan has the upper hand. So you can see that there's sort of a crossover point. If we're looking at 6 sales during any given day, Margot kind of has the edge because she makes so many more calls, even though her success rate is lower. Now, when we're talking about 8 sales, now Joan pulls ahead by quite a bit, because her success rate is so high and she makes 10 calls per day that she's going to have about 3/4 of those calls turn into sales, as we can see there. So you can see there are different things going on, and this is why I find these interesting. We have the probabilities and then of success, and we have the number of trials. And we can see those two distributions come into play. Okay, so just remember, even though Margot has a lower success rate in terms of making a sale, her greater number of sales calls per day overcomes the lower success rate when we're looking at 6 successes. Therefore, the greater probability of making 6 sales per day belongs to Margot, even though Joan's success rate is higher. So, the lesson about this is that the probability of any given outcome in this binomial distribution is a combination of both the number of trials and the success rate. So we'll keep that in mind as we do more problems involving the binomial distribution. Okay, so that wraps up our discussion of the binomial distribution, using 2 really good examples of how this is used in business and other applications. So, I want you to keep a couple things in mind. If you're watching this because you are having problems in your class right now, I want you to stay positive and keep your chin up. I have faith in you, and so should you. You can do it. The fact that you're on YouTube or wherever you're watching this, trying to learn more, that's what matters. It means you're making the effort to try to better yourself. That's what matters. Now, if you like this video, please give it a thumbs up. It does encourage me to keep making them. If you think there is something I can do better, please leave a constructive comment below. And finally, most importantly, I want you to keep learning and keep having fun. Learning is the best part of life. So once again, I thank you very much for watching, and I look forward to seeing you again next time.